Midterm will go through chapter 4, chapters 1, 2, 3, 4. It won't cover numerical methods. So the first half of chapter 4, you're going to be allowed to bring into class with you one sheet of paper, 8.5 by 11, both sides, anything you want on it, anything at all that you want. I'm going to pass out the data package, the tables, the graphs, the figures. When you turn the exam in, you'll turn the data package back into me. I'll keep those for the second, third midterm, and final exam. We'll talk more about that on Wednesday. Okay, where we left off last Friday. Yes, sir?
The packets that you're going to be passing out are already on Blackboard?
It's on Blackboard, okay. Right. So you know what you've got as resource there. Right, right. Here's where we left off last time. We were looking at table 4.2. We derived one finite difference equation in conduction. It was for an interior node. We derived that in class. That equation is in table 4.2. Table 4.2 also includes other equations, finite difference equations. For instance, case 2 is the internal corner node with convection. Case 4, external corner node with convection. Case 3, a node on a plane wall with convection. Our last case there, I'm going to erase this because it's covered at the bottom note. This is a plane wall with a uniform heat flux, Q naught double prime. So you've got 5 possible equations to use to set a problem up with finite differences. Now, if this covers heat flux on a wall, convection on a wall, what about the case where it's an adiabatic wall? Okay, what you do there is you set H equal to 0 in case 2, 3, and 4, or you set Q double prime equal to 0 in case 5. Let's just call that Q double prime. So that's, and we'll do that in just a minute, so an example problem. Okay, so we're going to work an example problem. We're going to look at this plate. This is a plate whose thermal conductivity is 25. We don't know how thick it is, but we do know it's 20 centimeters in this dimension, and it's 30 centimeters in this dimension. Our first goal is to set up a grid. So we're going to set up a really coarse grid, not one you want to do in the real world, but just to show you how the method works. So we're going to set a grid up of 10 centimeters. So you can see the nodal points, the big black dots. Those are the nodal points of my grid. The left-hand side is kept at constant temperature, 0 degrees C. The right-hand side is kept at a constant temperature, 100 degrees C. The top is kept at a constant temperature, 100 degrees C. Now, I could, like I did last time we met, number the nodes M and N, M column, N row. But that's too complicated for a simple grid like this. So I'm just going to number them, 1 through whatever. Oh, if I had 100 nodes, I'd use a double subscript. But for 12 nodes, I'm going to just call them 1 through 12. Node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there they are. The bottom is adiabatic. Question asked is, give me an estimate of the unknown nodal temperatures. Give me an estimate of the heat transfer Q. Okay. Let's start out with getting the temperatures. Now, some temperatures I know. By the way, there are 12 total nodes. 12 total nodes. I know T2 equal T3, T6, T9, T12 equal 100 degrees. I know T4, T7, T10, 0 degrees. Unknown. T5, T8, T11. So that's what we're supposed to find, those guys. Yes, sir.
I think it's T1.
Oh, T1, yeah, T1. Here's a game you can play with your non-engineering friends, okay? So you ask him, okay, now, why don't you give me your best guess? When x equal 2, what is y? Half the guys say 10, half the guys say 5. Wait a minute. Somebody's right and somebody's wrong? No, they're both wrong. That's okay. You can't ask that question. Illegal. Don't ask me. It was a good question. Thanks for asking. Otherwise, I wouldn't have done that. But I'm glad you asked. But no, illegal question. Don't ask me. I don't know, and I can't find out. What's that called in math? Discontinuity, discontinuous there, infinite jump, up from there. So anyway, here's what it means in our picture. As I approach the upper left-hand corner on the left-hand wall, the temperature is 0, 0, 0, 0, 0, 0, 0, 0. Approach from this side, 100, 100, 100, 100, 100, 100, 100. Get as close as you want, 100 and 0. If this were a copper plate in an electrical problem, where this was 0 voltage and this was 100 volts, that would be called a short circuit. All the current would flow, bam, to there. Nothing would flow inside, called a short circuit. You can't have that. So it's undetermined. You just say T1 is undetermined. I can't worry about it. Okay, fine, it's out, undetermined. Okay, is that all right? You kind of get the idea? Yeah. I'll say, in the real world, can this happen? No, you can't do that. You can't do that. What you do is you might put a little thermal insulation right there, a little piece of insulation right there, so they don't touch each other. That's the whole point. Don't let them touch each other. That's what you do in the real world. Okay, back to here. 3 unknown temperatures, which means I need 3 equations for 3 unknown temperatures. So let's take node 5. Node 5 is an interior node. So here's what I found out last time. For an interior node, here's what you do. You add the temperatures of the 4 surrounding neighbors and subtract off 4 times the temperature of the center node, and that should be equal to 0. Center node, T5. Surrounding nodes, 2, 4, 6, 8. Minus 4 times the temperature of the center node must equal 0. Node 8, interior node. Okay, add the 4 surrounding temperatures of the center node, 5, 7, 9, 11. Minus 4 times the temperature of the center node equals 0. Node 11, adiabatic boundary. I'll just say it's case 3 with h equals 0. Oh, here. 2 times T8 plus T10 plus T12. Minus 4 times T11 equal 0. You can get that from case 3 by setting h equal to 0. Plug in known temperatures to get okay, let's see what you got here.
On note 11, why did we add 2 of T8?
Okay, yeah. Adiabatic wall behaves like there was a T8 here and a T8 down here. That's why. So now add your 4 neighbors together. T8 plus T10 plus T12 plus T8, 2 T8s. It's symmetrical about the adiabatic wall, that's why, you know. Okay, now you solve it, I don't know, Excel matrix inversion, you solve it TI with the solver function or whatever. So it's pretty simplistic. There's 3 equations, algebraic, 3 unknowns, solve for them. When I do that, I get T1 63.5, or T5. I get T8, 53.8. And I get T11, 51.9. So that's my first estimate on the interior temperatures and the adiabatic wall temperature at the center. I know those are bad answers. I mean, the grid is way too coarse. If I want better answers, I'll make that grid a lot smaller. Say, okay, let's make, this is 10 centimeter grid. Let's make it 5 centimeter grid. There, 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 there. 5. Okay. I cut the grid size down by half. Unknown temperatures. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14, 15, 16, 17, 18, 19, is that right? 1, 2, 3, 4, 5, 6, 12, 18. Now you got 18 equations, 18 unknowns. Those answers now will be a lot closer to the real answers. You say, yeah, but I really want accurate answers. Okay, make the grid size 1 centimeter. Oh my gosh, hundreds of nodes now. You're solving a 150 by 150 matrix. Or on your TI, you wait overnight for 12 hours until it spits the answers out. Yeah, so what's the penalty you pay? More computing time. What's the good news? Better accuracy. Is it worth it? That's your call. You're the engineer. You figured out. What do you want? Where if I have the grid size, the temperatures don't change by more than 1/10 degrees C, okay, fine. That's your criteria. Keep going until you get there. So that's the kind of the game you play as far as what accuracy do you want. Okay, now, this is ME 4150, the title is heat transfer. So same old game. With conduction, once we get the temperatures, the next thing to do is to find out how much heat's transferred. From where to where? From the top and the right-hand side out the left-hand side. 100 degrees goes out the 0 degree face. So I'm going to find out how much heat we have. First, we'll look at Q that comes into the 0 degree face. All right, here's how we do it. Remember, we first talked about numerical methods in the grid. And we said you lump the mass at the nodes, and the nodes are connected by heat conducting rods. The only way for heat to be conducted is through the heat conducting rods. Okay. Here's a node on the 0 degree face. Heat comes in from the right-hand side. Heat goes from 5 to 4 through this heat conducting rod right there. Q 5 to 4. Heat goes from node 8 to node 7 through the heat conducting rod. Heat goes from 11 to 10 through the heat conducting rod. Now don't get confused. You say, yeah, but that's an adiabatic wall. I know, but remember what adiabatic wall means. Heat will not be transferred normal to the wall. I understand that. Can heat be transferred parallel to the wall? Sure it can. What's this temperature? 100. What's that temperature? 0. Of course there's going to be heat transferred along that. This is a heat conducting rod. Heat can't go this way, but it can go this way. Question over there?
Does that mean it's an isotherm?
Yeah. Wait, what?
The heat conducting rod?
No. No. I'll give you an example. That temperature is 100, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. It's not the same temperature. Oh, I'm glad you mentioned that. Thank you. I'm so glad you mentioned that. Because what I meant to do first was to draw the heat flux plot, just to give you an engineering interpretation of this. Heat flux plot. Okay. So here is our adiabatic surface at the bottom. I'll say T1 is here, T2 is here, T2 is here. Okay, geometric symmetry, yeah, right through the middle. Geometric symmetry, yeah, right through the middle, vertical and horizontal lines. Thermal symmetry, vertical line, T1, T2, no. Horizontal line through the middle. Adiabatic, T2, no. There's no lines with thermal symmetry. Conclusion, okay, I can't use that. All right, but here's something we did twice already. We said, you know, where two corners come together of different temperatures, the heat pretty much flows around, the closer you get, almost like a quarter circle, almost. So I know that one. At the bottom, this is adiabatic. Let's assume T1's hot, T2's cold. Heat comes in near the bottom of the hot surface T1. It can't get out the bottom. So it pretty much travels along here, somewhat horizontal, like that. Okay, there's an adiabat. Oh, that's an isothermal corner. I know an adiabat comes out of that corner and it bisects that corner. And then it has to go out down here or vice versa. Fill in the rest. There they are. These are the adiabats. Now we'll draw the isotherms. We did it twice before. The isotherms that come out of a corner where two different temperatures are there at the corner, T1, T2, they come out in a fan pattern. Like that. Okay, good. When the isotherms get to an adiabatic boundary, it says they come in at right angles. Okay. Everywhere inside the boundaries, it says they must cross at right angles. Okay, draw a few of these then. These guys are the isotherms. So that gives you a little bit of engineering intuitive feel for what's going on. Oh, if you want to get more accurate, you can construct curvilinear squares. He's real good. He's not bad at all. You can do that. And that'll give you an estimate of the heat flow, mk delta T over N. It'll give you an estimate of the temperatures in there if you construct reasonably curvilinear squares. So yeah, you can, but we're doing it now by numerical methods. But that's the physical picture of what's going on, which gives you some feel for the problem. Numbers on a spreadsheet do not give you a feel for a problem. Graphical things like that give you a feel for a problem. Why do you think Moore's circle is so important? You can do it by equations, and they're accurate to 15 places accuracy. Oh no, Moore's circle tells a great story, a phenomenal story, but you see it visually. It gives you that engineering intuitive feel for a problem. Same thing here. Okay, let's do it. Q5 to 4. Now, this heat conducting rod replaces that much material. 5 to 4. Here's the heat flow. What's the area? My hand. What's that? Delta Y times 1. The area is delta Y times 1. We're using chapter 1. Okay, K, the area. Delta Y times 1. Divided by the distance the heat traveled. Delta X. Okay. 8 to 7, same thing. K. Oh, put the temperatures in there. T5 minus T4. Plus K. Area, delta Y times 1. Delta X. T8 minus T7. Plus, now, you got to be careful. So, okay, let's do 8 to 7 first. There's 8 to 7. But now, 10, 11 to 10, the area is half of Y. So there it is. If we make the grid square, delta X equal delta Y, makes life easier. Cancel, 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 cancel. Oops, not K. Delta Y, delta X. I know K, 25. I know all the temperatures. Put them in there, and Q is equal to 360 watts. You say, yeah, but look at this picture. The 0 degree face is covered. We've covered that much of it, but we've ignored that much of it. We didn't account for that right there. I know. That's why it's because my grid's so coarse. If I want to get a better Q, I'm going to put more nodes in here. And I'm going to reduce this now to this much area that's unknown by having the grid size. If I have the grid size, this will be ignored. This will be accounted for. Say, yeah, but I want a better answer. Okay, make more nodes. Have it. Have the spacing. Now, you're ignoring this little piece. You get better and better estimate of Q as you make the grid finer and finer at the cost of what? Computing time. Okay, now, what comes out of the 0 degree face should have come in the top and right-hand sides. What comes in here in steady state should go out here. Okay, let's try that then. Q out of 100 degree face. All right, look at the heat conducting rods from 5 to 2, from 5 to 6. Okay, let's do 5 to 2 first. Well, Q 5 to 2. Plus Q 5 to 6. Plus Q 8 to 9. I'm sorry, it should be 6 to 5, 9 to 8, 6 to 5. We've got 5 there. So the hot temperature is 2 to 5, 6 to 5. 2 to 5, 6 to 5. And then we have 9 to 8. And then we have 12 to 11. I'm not going to go through that. Do it the same way I did it here. But it comes out to be 356. Yeah, I know they're not equal because my grid size is so coarse. I'm surprised it's that close, actually. I'm very surprised it's that close, actually. I mean, so what's my answer? Add them together and divide by 2, 358. That's my answer of what Q is. That's my approximate answer. The finer your grid size, the closer they're going to agree. But again, at the expense of what? Computing time. Is it worth it? That's your call. Okay. The finer you make the grid size, the more accurate your temperatures are, and the closer Q is to the actual Q. These guys here, no, that 9 means nothing. It might be anywhere from 50 to 50, 51 to 53, that temperature. Okay, any question on this then? Yes, sir.
Why do we start in between the boxes again?
Yeah, let's take 6 to 5. This rod replaces how much material? That much material. All the heat from here to here is called Q 6 to 5. It's replaced by a symbol, node 6 to node 5. How high is this? Delta Y. How far heat travel? Delta X. Okay, that's how you do it.
So is it just kind of like a like theoretical or not theoretical, but like how you're in between 2 to 5 and then 1 to 4? Like that's kind of like arbitrary.
Wait, 2 to 5 and what now?
So like they're in between 2 and 5 and then 1 and 4.
Yeah, right.
So that's just kind of arbitrary because it's just going to cancel out, right? Or
There's one here.
so like how high up, as long as it's just like equal to each other, it doesn't really matter because they're gonna.
What's equal to one another?
Like how you put it into the equation where like the delta y's and delta x's ended up canceling out as long as you're just like consistent with that spacing.
Yeah. Otherwise, things would change. You know, these would change. You want to make it life easy, so you try to make delta x equal delta y. Yes, sir.
So for finding the Q out of a face, you just use the adjacent nodes to that face. Right?
Here's what you have to do. You say, well, well, it looks to me like, how about heat going that way? I say, no, illegal. illegal. Heat only is transferred along heat conducting rods. Is there a rod from 5 to 3? No. Okay. Is there a rod from 5 to 6? Yes. From 5 to 2? Yes. All the heat's conducted along those guys. There, when you draw this picture, these are the heat conducting rods. Now, is that something else you had a question?
Yeah, so if you had even smaller nodes,
Uh-huh.
so say you had like 5 going this way,
Uh-huh.
would you use, so it'd be 1, 2, 3, 4, 5, would you just use 5 to 4?
Along here,
Yeah.
like the top?
Yeah.
Yeah.
Does that make sense?
Okay. 4 to 9, 3 to 8, 2 to 7, 10 to 9, blah, 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 blah. Yeah. Yeah.
So how come we ignore like 2 to 1 and?
Okay, I got it. Yeah, okay.
Sorry, I'm not sure if you made that clear.
Yeah, yeah, okay. That's a good question. What's the temperature here?
2 or 100.
What's the temperature there? What's the temperature right there? 100.
Even though the zero's coming in from that side.
The problem said the top surface is at 100 except the corner. That's what the problem says.
Okay.
Okay, yeah. It's got to say that. It's got to say that. Yeah. Over here, the left-hand face is 0. Where except right there, illegal.
I thought it was an assumption.
Yeah, no, it's gonna say it. It's gonna say it in the problem. Okay. Was there another question? Okay. Yes, sir.
If you draw the box for the area that it replaces for 6 to 5.
6 to 5. The original one?
Yeah.
Uh-huh.
And then if you draw the box for 2 to 5, they overlap slightly.
6 to 5. Yeah, 6. This was 5?
Yeah.
Okay. There's 6 to 5. Now, which one? Yeah, they overlap. Yeah, you got it. Right, right. Yeah, in a way. How about this area here? Conclusion, I ignored it. So I double count here, ignore that one. You know there's errors built in this thing. But guess what? As you keep reducing the grid size, they go away. The errors get smaller and smaller. The problem areas get smaller and smaller. That's right. Yeah. Uh-huh.
They only happen at the corner.
Uh-huh. Uh-huh. The corner starts to just, this area gets smaller. Now you're missing that much. Now you're missing that much. Now you're missing that much. At what cost? More computing time. Yeah. Okay. That ends our chapter on 2D heat conduction. Now, I'm going to go over some problems for homework. Did it get over to you guys yet? Homework? Okay. Oh, yeah. Let me answer me, please. Thank you. Did anybody come in late that didn't get their homework back? Okay. All right. Let's, just so you know the numbers on this 315, the main problems on that was getting the correct K values pretty much for that wall with studs, insulation, wall board, and siding. So the hardwood siding, K equals 0.094. Gypsum, zero, 3, 8. Insulation, 0. Oh, that's 0.38. This guy here is 1.7, gypsum 0.17. Area of the total wall, 2.5 meters high by 6.5 meters long. Area of studs, there were 10 studs. Each stud is 4 centimeters and 2.5 high. Each stud 4 centimeters by 2.5 meters. Area of insulation, area of the wall minus area of the studs. You need those areas, of course, for your resistance. Ka over L. There's your areas. If you didn't get these K values, see me after class and I'll point out exactly in the tables where the correct value is for you, so you know. 327. The correct answer for the chip temperature, 48.1 degrees C. I think I had down 46 point something degrees C. The correct answer is 48.1 degrees C. 3111 is a solar collector panel which behaves like a fin. There's two tubes carrying a fluid, generally water. X measured from here, L is halfway. There's convection coming out to the air. There's radiation coming in from the sun. Okay. And you go back to the way you start that problem is to go back to fins at the derivation of the fin equation for temperature, which is equation 361. And you have Qx minus Qx plus dx minus Q convection equals 0. That was equation 361. We did that in class. We took a small differential element of length dx out of the fin. We wrote that equation, energy balance on it. And from that, we got a differential equation relating temperature as a function of x. In words, heat coming in the left side of the element by conduction, Qx, minus heat going out the right side of the element by conduction, Qx plus dx, minus the heat lost by convection to the fluid at T infinity. Now, what's the difference here? You see the picture. The difference is I've got to throw in Q sun as an input. It's coming in. Coming in means positive. So this becomes plus Q sun equals 0. That's a constant. It's just a constant. Q sun's given as a constant. You then follow what I did in class or in the textbook on that page until you end up with an equation similar to the 366. Which is the governing differential equation. So it's a pretty straightforward solution. All you do is throw a constant in and then follow line by line, 5 lines, what he does in the textbook to get something similar to equation 366, which is a governing differential equation. Okay, 3149. This is, okay, this was the circular tube separated by, there's baffles here, there's baffles here. Okay, there's fluid flowing. This tube comes out of the blackboard. These are baffles. So the fluids flow in these 4 quadrants. So I have Q equal Q from the fins plus Q from the wall. These guys behave like fins. This is T base. T base, T base, T base. In the middle, No heat crosses horizontally, no heat goes up and down vertically. Conclusion, at this point, these fins behave as if they have an adiabatic tip. Case 2, table 3-4, find QF, got it. How many fins? 4, got it. Table 3-4, case B, plus Q from the walls. Q from the walls. Okay, what's the total wall area? The circumference times the length. Circumference, pi d. But you have to subtract out 4 times t, because that's not bare wall. The fin's touching the wall there. Times the length, which is 1. We'll do it on a per meter basis. So that's how you get that guy. Okay. 3,158. Any questions on him before I go on? Okay.
So the length of the fin, you just do the length of the surface touching the fluid, right? Not all the way to the center.
Yeah, that's right. I would go to that. Yeah, I would go to that. Yeah, because like you say, it's not touching the fluid there. Yeah. 3,158 is this picture. Circumferential fins. Okay. By the way, on this problem here, you don't need to find the fin efficiency. That's a waste of time on a timed exam. You can. If you're asked for it, you sure can. But this is the easy way out, because I know what QF is. Capital M, hyperbolic tangent, little ml. I can get that really quick. But if you want to find the efficiency, you can do it that way. It just takes more time. So on this exam, time is valuable, real valuable. Come up Friday. Okay, this guy. Let's check how many fins there are on that thing, 158. The first part says find the heat loss by 1 fin. Okay, got it. That's part A. Yeah, heat loss per fin, 200 fins. So I'm going to use table figure 320 to get eta fin. And then Q for 1 fin is equal to eta area of the fin times h t base minus t infinity. And the area of the fin, there's top and bottom. So area of the fin is pi 2, because there's top and bottom, times pi r squared minus the inside radius squared. There's your area of the fin. For 200 fins, Q total equal 200 QF plus Q from the bare wall. So there's the bare wall. Now I'll show you the bare wall. That's the bare wall. So how many spaces are there between the fins? 199. If you want to do it that way, it's fine. But be careful. He says the fins are spaced at 5 millimeter increments. Boy, I told you, in this chapter on the fins, there's so many different areas. There's A sub C, there's A sub P, there's A sub F. You got to know that most people on fins make their mistakes on areas, which should be the simplest thing of all, but they make their mistake on the areas. So the spacing of the fins, 5. 5 millimeter increments. A wall in your house, somebody tells you the studs are 16 inches, spaced at 16 inches. Does that mean there's 16 inches between this face and that face of the stud? No. What's the correct way to say that? Center to center, right? Yeah, center to center. So what does this mean? 5 millimeters, center to center. No, you got it wrong. Your area's wrong. It's from the middle to the middle. People make mistakes like that, which seems small, but when you multiply it by 199 spaces, it becomes rather large. So get the areas correct on problems like that.